ocean. Anyway, I want to talk to you a bit about southern New England lobsters and how we're trying to fit effects of climate change into our assessment model. Anyway, lobsters are found from Canada down to Virginia, North Carolina. They're cold adapted species, and their center of distribution is up in the Canadian Maritimes. Let's see. Oh, I just messed it up.
I don't know where the thing is.
No.
You got it.
All right. Use it. Forget it. Anyway, it's up in the Canadian Maritimes and the Gulf of Maine. And lobsters are managed by the Atlantic States Marine Fisheries Commission. John Maniscalco mentioned earlier they're a group, interstate group, that manages migratory species. And for American lobster, the states from Maine to Virginia are involved in management. We have two stocks. One is Gulf of Maine, Georges Bank, and the other is southern New England, which is everything south and west of Cape Cod. So this is a graph of lobster landings. So the inshore stock are the hash mark, and offshore is the solid one. Majority of the population, especially historically, was inshore. And you can see that the population hit a peak in the late 90s and then has continued to decline, and current landings inshore are actually below offshore. So the Atlantic States Marine Fisheries Commission is involved with managing and assessing the stock. And so we utilize information from landings information and abundance to use for assessment models. In 1999, we had a major lobster die-off in Long Island Sound. And it killed not even just lobsters, but also crabs and a number of other fish down on the bottom. January 2000, it was declared a federal fishery disaster, and funds were made available to do a lot of research to figure out what went on. So there was research looking at temperature effects on lobsters and effects from different diseases and pesticides and dissolved oxygen and other environmental variables. And what they found out is they felt that it was really a perfect storm. A lot of things got together to cause this major die-off. But the biggest driving force was increased water temperature. And so it had been, bottom temperatures had been increased a large area for a long amount of time before this die-off. In addition, a number of these lobsters were actually had this paramoeba infection. In the Eastern Sound, a number of lobsters had shell disease. Dissolved oxygen is also always a problem in the summertime, but temperatures seem to be the real driving force. So like I said, we do utilize information to do assessments. One of the pieces of information we use are indices of abundance. This is a spring trawl survey from a variety of places, both inshore and offshore. Spring data is pretty variable, probably due to lobsters moving in and offshore in the winter and spring due to temperature. But you can see that general increasing trend in the late 90s and then the decline to low levels. Fall data is a lot less variable, and you can see that increase and decrease again. We also utilize information from some young of the year surveys, so we can see what small lobsters are coming into the population. So up on the top left, we have a young of the year settlement index. Rhode Island has the longest time series, and it shows declined pretty much from the early 90s, but it's certainly at low levels in recent years. And we have larval index from Long Island Sound on the bottom right. And they tend to be very variable because larvae tend to be real clump distributions, but again, very low levels in recent years. So we're seeing the same sort of trends in both the adult and the larval inflammation. So we decided to look at what's going on with temperature, since it seemed to be a driving force from all the research done on the Long Island Sound kill. So what these graphs show the temperature anomaly, which is how different is each year from the long-term average. And so where those bars go down, that means those years were colder than the average, and where the bars go up, the years were warmer. And the data we're looking at is actually the number of days over 20 degrees C. So for lobsters, temperature in general doesn't seem to be affecting them, but there's a threshold effect. So once temperatures get to be above 19 degrees C, they tend to move away from that area. And once they become greater than 20 degrees C, they start seeing physiological effects. So they see effects on respiration and on the immune structures. The top is a long time series from Woods Hole, but that's surface temperature. But on the surface, we see that since the late 90s, water temperature generally have positive anomalies, much warmer than in the historic time series. The bottom right is bottom temperature. It's a shorter time series, but we wanted to make sure that the surface temperature really reflected what was going on in the bottom. And again, we see a lot of positive anomalies there. This data is Massachusetts, but we also have data from Long Island Sound, and this is from the Dominion Nuclear Power Plant. And again, we're seeing that since the late 90s, we're seeing mostly temperature, positive temperature anomalies. And this just indicates that most of the inshore area in particular in Long Island Sound has been seeing warmer than long-term water temperatures. As I mentioned earlier, once water temperatures get warm, lobsters tend to move away from that area. And this is some data from Massachusetts survey where they go out in commercial lobster boats. The map over on the top left shows data from 1998. And you can see that a lot of the fishery actually occurred inside Buzzards Bay. The depth is color-coded on this graph. So the lighter blue is shallower and the darker blue is deeper. So most of the fishery in the late 90s was in Buzzards Bay, which is a much shallower area, and a small fishery in Vineyard Sound, which was a little deeper and cooler. By the time we get to the late 2000s, that fishery has collapsed in Buzzards Bay. The lobsters just aren't there anymore and have moved out into that deeper water. You can see the darker blue. That's where the fishery is occurring, and off of Martha's Vineyard. The people in Massachusetts also did a survey. The lobster larvae are pelagic at first before they settle to the bottom. So what they did is they took surface drifters and they put a whole bunch right by Martha's Vineyard where currently all the females with eggs are. And they let them go during the time period that the eggs are hatched. And they saw that most of those drifters went south and west off the south shore of Long Island over to New Jersey. When they put the drifters in Buzzards Bay, which is where historically a lot of the fishery was, there's actually a gyre in there, a current gyre. And so those drifters actually stayed in Buzzards Bay, which indicates that historically, when the lobsters hatched their eggs, they would stay where the population was and would repopulate that area. But where it is now, those lobster, the larvae is just being ejected off the South Shore of Long Island. So the population is not being regulated. And we looked at recruitment, which is lobsters that are below the legal size limit and that are going to grow into legal size. And we related it with the number of degree days over 20 degrees, and we found a significant negative relationship. So as temperature increased, the recruitment decreased. And as I mentioned, we also saw a lot of shell disease, most of it in eastern Long Island Sound and Block Island Sound. Shell disease, the bacteria eat the shell of the lobster. Usually they can molt out of it, but if it gets very bad, they actually, if it goes through the shell, they can die when they're molting. It seems to affect the females with eggs the most, because females with eggs don't molt for a year. They hold their shell until they hatch the eggs. And so their shell's on longer, they get worse case of shell disease. But they also sometimes, if the shell disease gets really bad, they'll actually molt out of the shell just to get rid of it, but they lose all the eggs at the same time. So besides the fact that they might die if it's bad when they're molting, they also may just lose eggs and decrease their reproductive potential. Looking at shell disease, the graph on the left just shows the incidence in the sampling with the commercial fishery, and that's increased since the late 90s. And the one on the right, the dashed line is the incidence of shell disease, and the solid line is the number of degree days over 20 degrees. And so there does seem to at least be a correlation with the two, that we're seeing higher proportion of lobsters with shell disease since the temperature has increased. So the model that we're using is a length-based model, and we utilize information from the commercial fishery, what the landings are, the different lengths from the landings, information from those trawl surveys I showed earlier, plus the lengths. But some of the inputs are natural mortality. Most assessments, you just use one number for natural mortality, and that's how you model it. And so back in 2009, we used a natural mortality rate of 0.15, and that was just set annually for the model. And that relates to basically an animal that lives to 20 years, and that's how long a lobster would live. But we did a sensitivity run knowing that we saw this big decline and that we saw die-offs, dead lobsters, that probably some of that, some increase in natural mortality may have occurred. So we ended up just bumping up natural mortality starting in 1998 and ran the model. And we just chose a number, increased it a bit. And the model actually fit the data better when we increased natural mortality after that time period. So we actually ran the model with a whole bunch of different natural mortality rates during that time period from 98 on. And we found that basically almost doubling natural mortality during that time period, the model fit the data better. So when we ran the model again in 2015, we ran it with an increased natural mortality rate during that time period. And from what I know, I think this is one of the first assessments that actually has used a time-varying natural mortality in the assessment. And this just shows that's how we modeled the data. And we ended up doing a number of different sensitivities. Some of it was just ramping up over the years instead of that knife edge. Oh, sorry. Instead of knife edge, we ramp it up a few years, tried different time periods, but that seemed to fit the data the best. This is some of the model output. It has the base case with that increased natural mortality and different sensitivity runs. they all pretty much give you the same abundance, where you see that increase into the late 90s and that continued crash. And the current abundance level is the lowest we've seen in this time series, and we believe that the stock is seriously depleted. We also looked at recruitment, and we find that recruitment is the lowest we've seen in the time series. And frankly, when we were doing the model, it was difficult to get the last couple of years because it kept hitting the lower bounds, and we had to actually put in recruitment variables, covariates, and that's something that we can play around with, trying to see what's the best covariate to have the recruitment fit the model the best. But again, it's looking that recruitment is almost near zero at this point, and we feel that we've actually seen recruitment failure. And this is an interesting graph. This is model output spawning stock biomass versus recruitment. And if you look up on the top, it's actually, the line is by year. So up on the top left, it starts in 1980, and it goes around to the bottom left is the most recent year. And so those dots up on the top, you're seeing spawning stock biomass. You're getting a much higher recruitment level for a certain spawning stock biomass than you are in recent years. And if you look at the very end here, you see that recruitment is just plummeting at a similar spawning stock biomass. And so it's just, it seems that recruitment is just not responding to a different spawning stock biomass. And I just wanted to throw out is we're seeing a much different dynamic in Gulf of Maine, and I think we've heard about that earlier from the plenary session. But Gulf of Maine, we're seeing the abundance is just increasing dramatically. And when they look at recruitment, they actually regressed it with good days, which are between 12 and 18 degrees, and they're seeing a significant positive increase in recruitment with the good temperature. And some of the hypothesis there is that maybe they're just getting through a lot of the molts at small ages, and then decreasing natural mortality. But again, that's something that we can look in the model, because we're currently doing a new assessment, is investigate what's the effect of changing natural mortality in these two different stocks, which are showing really opposite dynamics. And I'd just like to thank my staff for all their hard work collecting the data, the Lobster Technical and Assessment Committees, because we all did this work together, and the commercial fishermen who help us with this information. Thank you.